All right, part 2 of graphing rational functions. This time we are adding finding zeros to our objectives. Let's get started. Right. Okay, so let's take a deeper dive into what this little information box is telling us. It says that if my rational function is made up of two polynomials, so P and Q are polynomials, right? And if I were to factor, nothing would cancel out. So it says that there are no common factors other than one. So everything is simplified down as far as it can go. There are two things that we can get from this type of rational function. First, we can find the zeros. And the zeros are going to be found by setting the numerator equal to 0 and solving. So it says that they're going to be at every real value of x for which p of x, remember that's the numerator, is equal to 0. So to find your zeros, we're going to set the numerator equal to 0 and solve. Okay, that is how you're going to find the zeros for the function. Now, our second bullet says that we can find vertical asymptotes at each real value of x for which for which q of x is equal to 0, and q of x is your denominator. So again, excluded values create vertical asymptotes, and we know that excluded values come from our denominator. So when our q of x is equal to 0, we find vertical asymptotes. So in this case, we will set our denominator equal to 0, and we will solve. All right, let's do it. So example 3 says, find the zeros and the vertical asymptotes of the function. Okay, so just so that we can remember, zeros are the places where your graph will cross the x-axis. All right, so where the graph crosses x-axis. All right, so that's what zeros are. So from our table earlier, we can find the zeros by setting our numerator equal to 0. Okay, so zeros. We are going to set our numerator equal to 0, and we are going to solve. All right, well, this looks like one thing that we can factor. So let's go ahead and factor. So we have that x minus 3 and x plus 1, and that gives us solutions of -1 and positive 3. So these are my zeros, are my x-intercepts. So I'm going to go ahead and plot them. So I have an x-intercept at -1, and I have an x-intercept at positive 3. Right, this is not enough information to graph. We're going to go and then find our vertical asymptotes. So vertical asymptotes are found by setting the denominator equal to 0. And in this case, this gives us a solution that x is equal to 2. So I'm going to graph my vertical asymptote at x equals 2. Okay, so there's my vertical asymptote. Well, you may be wondering, well, what does my graph look like? Now, the graph of this function is still a hyperbola. It has two branches, and it just so happens to look like this. I'm going to try to draw it. And there it is. Okay. Important for you to note is that zeros are found by setting your numerator equal to 0, and vertical asymptotes are found by setting your denominator equal to 0. All right, I want you to try it. I want you to find the zeros for this function and find the vertical asymptote of this function. And in full disclosure, I probably won't have you to graph one of these, but go ahead and give it a try, and we'll see how you do in the end. Take a look. Does your graph look like this somewhat? And are your zeros and vertical asymptotes correct? Great. All right, our next objective is finding horizontal asymptotes and then using those to graph rational functions. So now we found zeros, we found vertical asymptotes, but there are some specific and special cases that we need to consider to find horizontal asymptotes. And here they are explained in this summary. So it says, let f of x be a rational function where we have two polynomials in a ratio, okay? And it says that standard form, no common factors other than one, so that means that nothing factors or cancels. It says the graph of f has at most one horizontal asymptote. So that means that we can only have one horizontal asymptote at most, okay? So vertical asymptotes are a little bit different. You could actually have multiple vertical asymptotes, but for horizontal ones, we can only have one. Here's how we're going to find them. First, it says, if the degree of P, which is your numerator, is greater than the degree of Q, there is no horizontal asymptote. All right. For example, now we got to think back to degrees and polynomials. If I have 4 plus x squared over x as my function, then the degree at the top is a 2, and the degree on the bottom is a 1. This is a case where there will be no horizontal asymptote, where the degree on top is greater than the degree on bottom. I like to call this top heavy. Okay, top heavy. All right, our next case, and let's erase some of this. Our next case says that if the degree of P, the numerator, is less than the degree of Q, the denominator, then the horizontal asymptote is going to be the line y equals 0. So there's no calculation or anything to perform. If your numerator degree is smaller than your denominator degree, then you have y equals 0. So an example of that would be f of x is equal to, let's flip that same one over. 4 plus x squared now is on the bottom. So this is the degree of 2 on the bottom, and the degree of 1 is on the top. This is what I like to call bottom heavy. And bottom heavy. Okay. So then the last choice, all right, my last option says that if the degree of P equals the degree of Q, so that means my numerator and my denominator have the same degree, then the horizontal asymptote will be the line y equals whatever the leading coefficient of P is over the leading coefficient of Q. Well, let me explain. So here's an example of a rational function that has polynomials with the same degree. So I have x to the third plus 7 divided by 2x to the third plus 2x minus 1. So there's no factoring or canceling that can be had. And it tells me that since my degrees are the same, they're both 3, that my horizontal asymptote is going to be y equals the leading coefficient of P. Well, what's the leading coefficient up here? My leading coefficient in front of this is just a 1. And what's my leading coefficient in the one in the bottom? It's a 2. So then my horizontal asymptote is going to be y equals 1 over 2. This is my horizontal asymptote. All right, so it's going to be the ratio of those leading coefficients. I know this in words seems a little confusing. However, looking at these examples, hopefully you get a good understanding. All right, let's get into some examples. Let's get into some examples here of how to find our horizontal asymptotes. But not only horizontal asymptotes, but we are going to also find zeros and vertical asymptotes as well, because it says all asymptotes. So zeros are where we take our p of x and make it equal to 0. Asymptotes. Vertical asymptotes come from q of x, which is the denominator, equal to 0. And horizontal asymptotes, well, we have to analyze the situation of our graph using the table above. Okay, so we're just going to make ourselves a quick note here. Okay, so let's look at what we have here. Our numerator, well, I can't factor that and cancel it with what's here. So let's just go ahead, zeros. So we have x squared plus 7x plus 6. Hey, wait a minute. We did this one, didn't we? And we have x plus 6, x plus 1. And that gave us zeros at -6 and -1. And for our vertical asymptote, what we found was, well, x is equal to -3. For a horizontal asymptote, well, let's see what we have here. We have a degree of 2 on top, and we have a degree of 1 on the bottom. So then this is actually top heavy. So when we have a situation where it's top heavy, there is no horizontal asymptote, and I'll abbreviate. All right. And we did see that when we graphed it last time, there wasn't a horizontal asymptote. There was a vertical asymptote at -3. We had our intercepts or our zeros here, and the graph just kind of swung off like this. Oh, I missed it. And the graph just did that. All right. So there is no horizontal asymptote for this situation. Let's look at our second one. So here, if we're finding zeros, we take our numerator, x minus 1, set it equal to 0, and we get a 0 is found at x equals 1. Okay, that's good to know. If we're finding vertical asymptotes, we're going to take our denominator and make it equal to 0. And so we do have a vertical asymptote at x equals 0. So let's go ahead and graph it. Well, that's really just our y-axis. Okay, there's my vertical asymptote, and I have a 0 right here. Okay. And then the next thing we need to find is a horizontal asymptote. Well, let's think about what we have. So what we have in this case is a bottom heavy type of situation. And when we have a bottom heavy situation, we have a horizontal asymptote that is y equals 0. All right, so this is my horizontal asymptote. And we need to figure out what this graph looks like. So you may be thinking like, wait a minute, Ms. Bettis, we have an intercept at 1, but we have an horizontal asymptote that's also at y equals 0. And that intercept is on the horizontal asymptote. Well, if we were to plug in points for this function or use a graphing calculator like Desmos to help us graph it, I want to show you what this graph is going to look like. Graph of our rational function. Notice we have that vertical asymptote at 0. So the graph just curves down, never crosses. But take a look at the horizontal asymptote. So on the left side of the graph, we recognize that horizontal asymptote, this branch of the graph is approaching, but it will never cross 0. But look at what happens on the right side of the graph. So it crosses that horizontal asymptote, but then it levels off again. So it's important for you to understand that horizontal asymptotes are the lines on the graph that as you go out to infinity, that graph will never touch. So the branches of our graph may violate the horizontal asymptote at some point, but as you go off to infinity, it won't ever cross at the ends. Okay, so it's still a horizontal asymptote for us. It crosses, that is our 0. Okay, and this is our vertical asymptote, and that's how the graph looks. Last example C. Now this is a fun one. I like this one. All right, so we have here 2x squared minus 2. Well, you know what? This can be simplified a little bit. So let's go ahead and factor, see if anything cancels, and proceed with what we know to do. So this bottom can be x minus 2, x plus 2. The top, we can go actually further, -1 plus 1. Okay. Well, and this will actually help us when we are trying to solve for our asymptotes and our zeros. So let's do it. All right, so nothing will cancel. Perfect. Let's go for our zeros. And zeros are found when our numerator is set equal to 0. So we already have it factored, which is nice. So this gives us solutions of plus and minus 1. All right. Vertical asymptotes when our denominator is set equal to 0. Already factored, makes it nice. So then our vertical asymptotes will be found at positive and -2. This time we have 2 vertical asymptotes. So this graph is going to be interesting. And the last thing we need to look for is a horizontal asymptote if it has one. And according to our rules, because our degrees are the same, so these are both second degree, we're going to go with the ratio of the coefficients. And so my numerator coefficient is 2. My denominator coefficient, leading coefficient, is 1. So my horizontal asymptote is found at y equals 2. All right, let's put this wonderful information on our graph. So I have intercepts or zeros at -1 and +1. I have vertical asymptotes at -2 and +2. And lastly, I have a horizontal asymptote at +2. Again, in full disclosure, I'm probably not going to ask you to graph these without the assistance of some type of graphing calculator. So don't worry about that. Just knowing where these features are found is going to be the very most important part of this whole process. All right, so if you wanted to know what the graph of this looks like, I'll just go ahead and sketch it for you. Like I said, you would use Desmos or something to help you do it. So there's a branch here. There is a branch over here. And there is a third branch here. Look at that. All right, so 2 vertical asymptotes creates for us 3 branches. All right, there you have it. Now let's have you all try some on your own. All right, so let's take a look at how you did. Pause the video, check your work, and let's go. Try it question. We had those 2 asymptotes, vertical asymptotes, really close together. And way, way, way up here, you'll find the third branch of the graph. And down at the bottom, it just looks like, there's nothing in between. But there is. So these rational functions have lots of action happening when you are graphing them. Again, there are 3 branches. And our asymptotes are found or were found at, I think, 3 and -3. Yeah, 3, +3. Here are the 3 branches of that second rational function graph. Here is the graph of the third try it question. Going to forge ahead and finish these notes out. Our last objective is graphing rational functions with holes in them. And a hole is also known as a discontinuity. And if you're coming to AP Calculus with me, please keep that phrase in mind. All right, holes in graphs. If a rational function has the same factor, x minus b, in both the numerator and denominator, then there is a hole in the graph at the point where x equals b, unless the line x equals b is a vertical asymptote. All right, so let me just explain what that means. So we are going to now factor and look. Ooh, that's not look. We will factor and we will look for binomial factors. Common binomial factors. Okay, so if I look at the first example, I have f of x equals x squared minus 4 divided by x plus 2. So let's go ahead and factor this. So x plus 2, x minus 2 on the top, and I have x plus 2 on the bottom. So here is what I'm talking about. There is a common factor. Okay, so then when I simplify, my function is now just x minus 2. And x minus 2 is really just a line, right? But because it started off as a rational function and that x plus 2 factor canceled out, that means that I am left with a whole at x equals negative 2. Okay, so it came from the factor that was canceled, is where my whole exists. Okay, so then let's look. If we were to graph this, we would start at negative 2 because that's our y-intercept. And then we would have a slope of 1. So we'd go 1 and 1 and 1 and 1 in this direction. And we would go this way also, but at negative 2, there is actually a hole. So it doesn't include negative 2. And our graph would look like this. There's a hole. Okay. All right, let's move on. Let's do this other one. Okay, it says you try it. I want you to factor, see if anything cancels, figure out if there is a hole, where it is, and create the graph. All right, let's do it. All right, take a look. How did you do? Here I have a common factor of x minus 2. That leaves me with x plus 3 as my function, which has a hole at x equals 2. All right, that concludes our lesson.